Welcome to our introduction to titrations. Our objectives today, we're going to review acid-base neutralization reactions. We're going to look at those reactions at the molecular level. We're going to describe how we can use mole ratios to quantify neutralization reactions. We're also going to describe how we can use titrations to determine concentrations of unknown acids or bases. And then we're going to wrap up with a calculation of concentrations and pHs given data from titrations. So first up, let's remember what are neutralization reactions. When we have acids and bases, we're going to neutralize them with each other and we end up with some salt and some water. So this one, hydrochloric acid and sodium hydroxide, let's write that acid-base neutralization reaction. HCl and NaOH, hydrochloric acid and sodium hydroxide, produce. We're going to make salt. The sodium and the chlorine are going to combine to make the salt. And then we also have an H and another H and an O. That's two H's and an O, that's water. So hydrochloric acid and sodium hydroxide combine to form sodium chloride, that's our salt, and water. Nitric acid and magnesium hydroxide also react to produce salt and water, but they're a little bit different. Nitric acid does not start with a hydro, which means that it's coming from our polyatomic ion list. It comes from nitrate. H turns into ic when we name our acids. Nitrate is NO3 with a -1 charge, which means it gets one hydrogen. And magnesium hydroxide. Hydroxide has a charge of -1. Magnesium has a charge of +2, so we need two hydroxides to balance out that magnesium. We're going to produce magnesium and nitrate. Magnesium, nitrate, magnesium still has that charge of +2. Nitrate has a charge of -1. So I need two nitrates to balance out the charge on the magnesium. And we also make water. Magnesium nitrate is our salt. Here's our water. I have two nitrates here, so I need to put two nitrates in my reactants. I now have two hydrogens and two hydroxides, and we can use that to make two waters. Last up, I have this crazy giant molecule. This is hydrogen. This is one of my polyatomic ions. This is known as acetate. So this is acetic acid because ate becomes ic when I throw a hydrogen in front of it to make it an acid. So this is acetic acid, and this is known as sodium hydrogen carbonate or sodium bicarbonate. It's also known as baking soda. And you might have guessed already that acetic acid is also known as vinegar. Classic chemistry, vinegar and baking soda. So our HC2H3O2 and NaHCO3 vinegar and baking soda are going to make. We're going to trade the sodium and the hydrogen. We're going to get NaC2H3O2. This is sodium acetate. And what's left over, this hydrogen jumps onto that hydrogen carbonate. We get H2CO3. You might be thinking, wait, we're supposed to make salt and water. Yes, we're going to make water. So this compound right here, carbonic acid, is going to spontaneously decompose because it's super unstable. It's going to decompose into carbon dioxide. Those are the bubbles that we see when we mix baking soda and vinegar. The other thing that we make is water. There it is. Here's our salt, sodium acetate, and here's our water. And we get bonus carbon dioxide bubbles. So we can look at this idea of neutralizing acids and bases with each other by remembering how acids and bases dissociate or break up in water. So our hydrochloric acid is going to pop apart into hydrogen ions and chloride ions. Sodium hydroxide is a base, is going to pop apart into hydroxide, polyatomic ions, and sodium ions. What happens when we mix these guys together, the sodium and the chlorine bind to each other, the hydrogens and the hydroxides bind to each other. And so this H plus thing that makes the acid an acid isn't there anymore because it's in water. And this hydroxide thing that makes the base isn't there anymore because now it's in water. And we're just left with salt water basically. So let's think about quantifying our neutralization reactions by looking at some mole numbers. So think about if I have 6 molar hydrochloric acid, that's pretty strong acid, right? That's quite concentrated. I want to know how many moles of hydrogen ions there are if I have 1 liter, that's 6 molar hydrochloric acid. Remember that our formula for molarity is moles over liters. So if I have 6 molar hydrochloric acid, I have some number of moles of hydrochloric acid in that 1 liter. Let's solve for x. We're going to multiply both sides by 1 we can do that in our heads, no calculators needed. X is going to give us 6 moles of acid, which means that I've got 6 moles of hydrogen ions because hydrochloric acid has 1 hydrogen in it. Same idea, but now let's think about how many moles of hydroxide are present in 1 liter of 6 molar sodium hydroxide. So again, we're going to look at 6 molar sodium hydroxide. How many moles of hydroxide do we have in that 1 liter? Again, X is going to be equal to 6. And because I have 1 hydroxide in every 1 sodium hydroxide, we end up with 6 moles of hydroxide polyatomic ions. So when I mix these two guys, my 1 liter of 6 molar hydrochloric acid and my 1 liter of 6 molar sodium hydroxide, those 6 moles of hydrogen ions and those 6 moles of hydroxide polyatomic ions definitely make 6 moles of water. And so again, we're just looking at how those equal numbers of hydrogens and hydroxides can balance each other out, and we end up with water instead of acids or bases. And that's exactly what titrations are all about. So in a titration, we're going to figure out the concentration of some unknown acid by titrating it or neutralizing it with a base of known pH and known concentration. So basically what I'm doing is I'm taking, I don't know how much hydrogen in my hydrochloric acid, but I'm going to mix it with my hydroxide until I have completely neutralized all of that hydrogen. And just like on the previous slide where we had 6 moles and 6 moles, if I can figure out how many moles of hydroxide I need to neutralize all of those hydrogens, then I know how many hydrogens we have. Titration setup is right here. This guy is called a ring stand. The ring stand has a clamp on it. The clamp holds onto the burette. Sometimes we spell burette with 2 T's and an E. Both ways are correct. We're going to put in this our standardized, we're going to call it the standardized solution. And it can be base or acid. We're going to do it with a base in our burette. It's called standardized solution because we know what the concentration is. So standardized means that the concentration, the molarity, the pH are all known. Standardized because we know what it is. This awkwardly named little nozzle here at the bottom of the burette is called the stopcock, and we're going to turn it. And when we turn it, we open up a little valve inside, and the base can drip down into the acid or whatever else we have down here that we don't know. And that acid is going to be combined with some kind of indicator. We're going to use phenolphthalein. What's super cool about phenolphthalein, it is colorless in an acid. It is colorless in an acid. But as soon as this acid has been completely neutralized by all the base, that one last little drop of base that we drip into the solution is going to turn the whole thing pink. It'll turn pink in a base. And that's when we know to stop. We're going to measure the volume of the base that we used and then use that to figure out what the concentration of our acid is. Burettes can be a little tricky to read, so we're going to zoom in on a burette here. Notice that the numbers actually count down, not up. So with our graduated cylinders, we're used to having 1, 2, 3, 4, 5 all the way up our graduated cylinder, but now we're going to count down. So what we do is we fill up our burette all the way to the top. We open the stopcock and the base will pour out, and then we're going to notice how far down the base in our burette went. And if we started at 0, then I can use this number right here. If this is 7 and this is, if that's 7 and that's 6, sorry, and that's 6.1, 6.2, 6.3, 6.4, 6.5, 6.6, 6.7, 6.8, 6.9. So we went all the way down to 6.9 milliliters. That means that 6.9 milliliters was dripped out of the burette and put into the flask under the burette. So just be careful, make sure that you're reading down, not up. Good? All right. So let's look at some data from our titration. So I've got 10 milliliters of hydrochloric acid sitting here. So we've got 10 milliliters in our flask. We're going to add that phenolphthalein to it. I need that 6.9 milliliters that I saw in my previous slide. So I went from 0 down to 6.9, so 6.9 milliliters of base dripped down into my acid before it was neutralized and turned that little bit of pink. I know that the concentration of the base that's in my burette is 0.1 molar sodium hydroxide. This is all the data that we need in order to calculate the molarity and then the pH of the hydrochloric acid that was here in the flask. We're going to use our dilution formula, but instead of having an initial solution and then our diluted solution, we're just going to put acids on one side and bases on the other. And it doesn't matter if you put base here and then acid over here, as long as you have the acids together on one side, the bases together on the other. So I've got 10 milliliters of hydrochloric acid. I'm going to call that V1. Unknown molarity is my M1. This 6.9 milliliters is my volume of the base. I'm going to call that V2. 0.1 molar is the molarity of my base. I'm going to call that M2. So for this question, I'm using 2 for base, 1 for the acid. So when we do V1 M1 equals V2 M2, V1 is 10 milliliters. Molarity 1, I don't know, that's what we're going to solve for. V2 is 6.9 milliliters and M2 is 0.1 molar. To solve for M1, I'm going to divide both sides by 10 milliliters. That cancels out there. Over on the right side, my 2 milliliters cancels out, and I can multiply 6.9 times 0.1 divided by 10. My friends, we can do this in our heads. No calculator needed. If I have 6.9 times 0.1, that's the same thing as moving my decimal backwards one place. 6.9 times 0.1 is 0.69. Divided by 10, if I divide by 10, I'm going to also move the decimal back one more spot. Throw a 0 in there, and my final answer is going to be M1 equals 0.069. And then the unit label is only molar because our milliliters canceled out, top and bottom. This is the concentration of our hydrochloric acid. And if I want to find the pH, and I definitely do want to find the pH of this acid, all I have to do is remember that pH is equal to the negative log of the hydrogen ion concentration in the acid. In this case, our concentration is 0.069 molar. I do need a calculator for this one. So negative log of 0.069 gives us a grand total of 1.16. So this is the pH of that unknown hydrochloric acid, and this is the molarity of that unknown hydrochloric acid. Easy peasy. Good? Good. I'm going to have you do this one in the Ed puzzle all by yourself. Come back and check your answers when you're ready. All right, so you should have done V1 or V2 for this guy. M1 here. This is our V2. This is our M2. So we're going to do V1 M1 equals V2 M2. V1 is 25 milliliters. M1, I don't know what that is yet. V2 is 12.5 milliliters. M2 is 2 molar. So now to solve for M1, we're going to divide both sides by 25 milliliters. That cancels out. M1 equals 12.5 times 2. That's 25. 25 divided by 25 is 1. And so our concentration of the acid is 1 molar. This makes sense because I needed half as much of my base as I needed for my acid. And my base was 2 and needed half as much, so the acid must be half as strong. And it is. It's 1 molar instead of 2 molar. To find the pH is going to be the negative log of this concentration. Negative log of 1 is 0. The pH of this acid is 0. Go ahead and do this one also on your own, and then come back and check your answers. Here's our V1, here's our M1. So this time the base gets the 1s. Here's our V2, M2 we don't know yet. And so V1M1 equals V2M2. V1 is 54 milliliters. M1 is 0.1 molar. Set that equal to V2 is 125 milliliters. And M2, I don't know what that is. Divide both sides by 125 milliliters to cancel that out. Milliliters cancels out over here on the left with our calculator. 54 times 0.1 divided by 125 gives us a grand total of 0.0432 molar. Do a sig fig check, and it looks like we only get to keep one sig fig, so our final answer is 0.4 molar. pH is going to be the negative log of that concentration, 0.04. Negative log of 0.04 gives us 1.4 is the pH of this acid. We're going to look at one more chunk of practice problems, and then we're calling this lecture done, my friends. So sometimes I'm going to give you data instead of a word problem. And what's interesting about trial 1 with our titrations is we always throw it out. We never use trial 1 data to calculate concentrations. And the reason is this: most of the time in the lab, the first time that you get to pink, you probably are going to make it too pink. So what we do with this data is we remember to slow way down just before we get to 6.70, and then we're less likely to overshoot or make too pink our solution in the flask. So we're going to throw out trial 1, but I did use this to make sure that we didn't go too far in trials 2 and 3. To figure out the volume of base that we used in trial 2, I have to do some subtraction. So I didn't fill my burette back up to 0, but instead we started at 6.70 and we dripped down to 13.35. To find the volume, we're just going to subtract 13.35 minus 6.70, and that's going to give us 6.65 milliliters. We're going to do the same thing for trial 3 now. 20 minus 13.35. 20 minus 13.35 gives us, hey, 6.65 milliliters again. So if these numbers were not exactly the same, I would have us average these two and use the average as our volume of the base. But since they're the same, we can just use that number. So we're going to do M1V1 equals M2V2. I'm going to make base number 1 this time, and acid can be number 2. Again, you can flip them back and forth. Either way, it doesn't matter. So my base, my molarity of the base is given to me up here in the question. So the molarity of the base is 0.10 molar. The volume we just decided with our math is 6.65 milliliters. Set that equal to M2 of the acid. I don't know yet, but the volume is given to me right here. So we had 20 milliliters of hydrochloric acid in our flask. Solve for M2 by dividing both sides by 20 milliliters. Milliliters cancels out top and bottom. We're left just with molar for our unit label. To calculate, we're going to do 0.1 times 6.65 divided by 20 gives us an M2 equal to 0.03325, and my unit label is going to be molar. We're going to check some sig figs. It looks like I get to keep 2, and so my final answer will be 0.033 molar. To calculate the pH of that guy, we're going to do negative log of 0.033 molar. Negative log, sorry, pushed the wrong button on my calculator. 0.033 gives us 1.48 is the pH. And my friends, we did it. We reviewed acid-base neutralization reactions. We talked about how those happen at a molecular level. The hydrogen from the acid, the hydroxide from the base find each other and make water. We described how we can use those mole ratios to quantify neutralization reactions. If I have 6 moles of hydrogen ions and 6 moles of hydroxides and they squish together to make 6 moles of water, then I have quantified with some mole ratios. We described how we can use titrations to determine the concentration of unknown acids or bases, and then we did exactly that with some calculations. Good work today.